So then we move on to linked lists. Now, it is interesting that we just did stacks and queues, and pretty well always in teaching this you learn linked lists first and then stacks and queues. But so we've gone a little bit ahead of things and we're working backward to focus more on linked lists. But basically you cannot implement stacks or queues unless you have ultimately a linked list implemented. But the order doesn't matter. Linked lists. Describe the features and characteristics of a dynamic structure. Any video? No video. So I will do this one in Photoshop. That the advantage of a linked list, the advantage of a list is, there's one main advantage, and that is that it's dynamic. If we have an array, we define the array from the beginning. We say the array is 5 ints. And when it's 5 ints, it's 5 ints and always will be 5 ints, and it can never be more. And if we're not filling it up, if we only fill up the first couple of parts of the array, then we waste the rest. Static. Arrays are static. And static is not good. Static is not good because quite often we waste unused memory. Whereas lists are dynamic. Dynamic. And by dynamic, we mean they can grow. So a list that has one element takes up that much space. A list that has 2 elements takes up that much, and there is no wastage. Because the lists can grow and they can shrink. So if we no longer need these last 2, then we get rid of those 2. And we're not wasting the memory. So lists are dynamic, they can grow and they can shrink. That's it. Oh, should understand the concept of nodes and pointers. So in order for them to grow and shrink, they have to be able to find each other. So this node needs to know where that node is, and that node needs to know where that node is. And the way we do this is by having a node be 2 parts. One part is the data, and the other part is the pointer. And there are notes in this, but just so I can talk through this, that you can't have a list unless you have structures that are made up of both of these things. So this could be numbers, 2, 4, whatever. But this is the important part, because this is the part that knows, so it would be like this, that knows where the next one is. That knows where the next one is. Okay, data and pointer. Whereas in an array, you just need the stuff. Because to find the stuff, it's just next door. If I want to find the 3rd element in an array, I just know this is where the array starts, and if it's an array of ints, I go 32 bits, 32 bits, 32 bits, and I will find the beginning of my 3rd int, because they're all next to each other. Whereas in order to work the way that lists work, they're scattered through memory. So each part of each node, or a part of each node, needs to know where the next node is. Describe how linked lists operate logically. I think the best way to do this is to look at point 13, because 13's got a bunch of different ways that they operate, and
drawing the following.
okay, I think what I've done here in the video is I've constructed all these. So I don't have to take that much time with this video because there's a video there already. But what I'll do is talk through what I had done. So this would be like the 3 or 4 minute version. If you want to get the 6-minute version, it's there. So how do they operate logically? You should be able to sketch diagrams adding to a linked list, deleting, modifying, and searching. And I think you two could probably in the 14 around the table could come up with how this works, but here's my explanation of it. Adding to a linked list. Well, you had this pointing to that, that pointing to that, and if we wanted to make a new one, or if this was the end of the list, then its pointer would be null, not pointing anywhere. All you do if you're going to add to the list is you make this new node, and you set the pointer of the former tail to be the new one. And the new one will have null as its pointer. So 2 things happen. Step 1, pointer points to the new thing. Step 2, because you got to keep track of where tail is. Tail changes. Tail is no longer this one, tail is that one. And why do you need to know where tail is? In case you want to add to another one, because you need to know where to add it on to. Deleting is a little bit trickier, certainly trickier when you're coding it. Originally, 1 pointed to 2, pointed to 3, pointed to 4, for example. But now we just want to skip this one. So the pointer from that one will point to the pointer of the one that it was pointing to, which makes for some really neat code if you take a look at the code of it. But basically, that skips over and points to the next one in line. Well, in fact, that's what the code looks like. It points to next.getNext. And that's where it gets really quite cool, but a while to explain, and I'll probably say it in a video at some point. But effectively, if you were to draw that diagram on an HL exam, that's how you skip. That's how you delete. In fact, how you delete is by skipping over a node. Modifying the data held in the link, well, really, it makes more sense to do the searching first, so I'm going to do the searching first. If I'm searching for Bob, it's sequential. I say, is this Bob? No. Okay, get the next. So I get the address of the next one and I look. Is the data part of the node Bob? No. If it's not, then I get the pointer for the next and I look at the data of it. Is the data of it Bob? Yes, it is. Then I found it. And usually it'll be a list of objects, and so there will be other associated information, so I can say, how old is Bob? And I'll know because I will be at that node, so I return the age, for example, attribute of that object. So it's sequential. How do you search for an item through a list? You start at the head and you work your way through to the end. It's sequential, which means it's not binary, and that speaks toward what we're going to do next when we do trees. Because yes, lists are efficient memory-wise, because you don't waste memory like an array does, but you cannot search them binarily, which you can within an array. So you wait till we get to the tree. The tree is the best of both worlds. That's giving away a huge secret early, but done. And then if you're going to modify it, it's a search. We want to change Bob to Charles. Is this Bob? No. Is this Bob? No. Is this Bob? Yes. Change it to Charles. That's it. Oh, and then we need to see different kinds of lists. Yeah, so a single list, one element points to another, points to another, points to another, and at the tail it doesn't point anywhere, so you can only work one way through it. That's a single linked list. A double linked list, you can work your way back. So you can work your way one way and the other way, because there's a pointer pointing to the next, pointing to the next, pointing to the next, but there's also another pointer pointing back. And a circular, it's only the tail which points to the head. So you can work your way through and go back to where you began. Is any of this applicable to your dossier? Not really. Not any more than what we've already done. I mean, you might think of a case where you want to work back and forth or where you want to delete. So I guess the one thing, for example, instead of just adding a NQ and DQ, you could have a find, and you could go further with this to overwrite what the find was, or make a find, or any of the other things that we just looked at. You could implement those, and that would be that you want your 12 out of 12 for sophistication. That would get you it. But this is primarily what I've just gone over, and will continue to do for a little bit, for HL examinations, not the dossier. There's actually a question back there at number 12. So that is how linked lists operate. And next we'll move on to the wonderful tree structure.